In this lesson, we're going to discuss scientific notation, which is a method that scientists use to represent numbers that are very large or very small in a more convenient and compact manner. Scientific notation takes advantage of the rules of exponents. An exponent is a small number that's written as a superscript to a base number. So for example, 2 is our base here, 1 is the exponent. We would say this is 2 to the 1 power. What that exponent is doing is it's telling us how many times to multiply the base by itself. So if we have 2 to the 1 power, that's just a 2. 2 squared, or 2 to the 2 power, is 2 times itself twice. 2 times 2 is 4. 3 to the 2 power is 3 times 3, that's 9. 2 to the 6 power is 2 times itself 6 times, for a total of 24. And then a special case, 2 to the 0 power is 1. In fact, anything to the 0 power, any arbitrary number to the 0 power, is 1. Another rule of exponents is a negative exponent. Our standard exponents look at how many times the number is multiplied. If you have a negative exponent, it's telling you how many times to divide by the base. So 2 to the negative 1 power, the negative power means that we're dividing by 2 to the 1 power, and 2 to the 1 is 2. 2 to the negative 2 power means that, again, the negative means that we're dividing by it, and we're dividing by 2 to the 2, which is 4, and so forth. So how can we take advantage of these rules of exponents when we are representing very large or very small numbers? Well, we use a base 10 system, which means that each column represents a power of 10. This is the ones column, that's 10 to the 0 power. The tens column is 10 to the 1 power. The hundreds column is 10 to the 2 power. And the thousands column is 10 to the 3 power. What that means is that moving the decimal place, the decimal point one place to the left, is equivalent to dividing by 10. So for example, if I take 3,127 divided by 10, I would get 312.7. I've effectively moved the decimal point, which was originally here, and I've moved it one place to the left, which is what we're seeing right there. If I take my 312.7 and divide by 10, it's as if I've moved the decimal point another place to the left. And so what we're going to do is take a very large number that has some significant figures and some placeholders, and we are going to focus only on the significant figures. Those are the only values we actually want to keep. One of the benefits to scientific notation is to allow us to drop all the placeholder numbers. So in this case, I'm going to keep only the first 4 digits. The last 2 are placeholders. The second thing is I want to focus on the most significant digit, the most important digit, the largest digit, right? The largest value is going to have the biggest effect on the overall value of the number. And so what I want to do is move the decimal point until it is just after the first digit. So I want to put my decimal point here. In order to do that, I have to move the decimal place from its original location. In this case, I have to move it 1, 2, 3, 4, 5 places to the left. And what I said was moving the decimal place to the left is the same as dividing by 10. So if I've moved the decimal point 5 places to the left, it means that implicitly I've divided by 10 5 times, or I've divided by 10 to the 5th power. In order to maintain the value of my of this number, if I'm dividing by 10 to the 5th, what I have to do to cancel that out is explicitly multiply by 10 to the 5th. So this part here is part of moving the decimal point. This part here stays to cancel out the change in value. So what I end up with is 1.409. Those are the significant figures from that value, times 10 to the 5th. This is a much more compact way of expressing this number. It keeps only the significant figures. I've dropped the non-significant figures, so there's less writing, there's less chance for me to make a mistake and miscount the number of zeros I've put there. And I have a power of 10 here to give me an order of magnitude to show how big this number is. Take a moment and pause this video and try to convert this number into scientific notation. Again, we look for the significant figures. There's an implicit decimal point here. There's no explicit decimal point written. So we start from the right and move our way left to find the first non-zero digit, and we see that these two are our significant figures. We know that we want to end up putting the decimal place after the biggest number so that we can focus on the most important part. So we're going to end up with a 4.3. These are our significant figures from the number with the decimal point after the largest value. Then we look at how far we would have to move the decimal point. There is an implicit decimal point at the end of this number. To move it where we want it to go, we would have to move 8 places to the left. Moving it 8 places to the left would be the same as dividing by 10 8 times. And so to cancel out that operation, to maintain the value that we're talking about, we would multiply by 10 8 times. This is scientific notation for a large number. Notice that we have positive powers of 10 for these large numbers, representing large values. We can use the same method for very small numbers. If we have a number that is less than 1, if we multiply by 10, we move the decimal point 1 column to the right. So moving the decimal place to the right is the same as multiplying by 10. So we can do basically the same thing we did before, but in the opposite direction. When we have very small numbers that have a lot of zeros here as placeholders to give us very small quantities, we can use scientific notation to eliminate these placeholders and focus on the important points. Again, what we're going to do is to focus on the significant figures of the number. In this case, we have a explicit decimal point written right there. And so we're going to start from the left and move our way right until we find our first non-zero value. And that and everything to the right of it are going to be significant values, significant figures. So in this case, we're going to end up with 848 are the numbers we want to keep. Then we want the decimal point to be just after the first digit so that we're focusing on the most important quantity, the largest quantity. So we want the decimal point to be between the 8 and the 4. We want it to be there. But to get it there, we have to move 4 places to the right. And we just said that moving 4 places to the right is the same as multiplying by 10 4 times. So if this motion here is the equivalent of multiplying by 10 4 times, or multiplying by 10 to the 4, what we need to counteract that is to then divide by 10 to the 4 to cancel it out. But if we're dividing by 10 to the 4, we'll use the other rule of exponents that we saw at the beginning of this lesson. Instead of dividing by 10 to the 4, we will multiply by 10 to the negative 4 power. So here, multiplying by 10 to the negative 4, the negative exponent means that we're dividing by 10 to the 4, which is what we were talking about here. Again, pause this lesson and take a moment to write this number in scientific notation. Here, again, we have a explicit decimal point, so we'll start from the left and move our way to the right until we find the first non-zero digit. That and everything to the right of it are going to be significant. So in this case, we'll have 160. All of those that are to the right of that first non-zero digit are significant. That 0 is there because we must have measured it and gotten 0. If we didn't measure to that level of precision, we would have just omitted the 0 at the end. I've put the decimal point after the 1, after the largest value. And then I look, this is where I want the decimal point to be. This is where it started. So I must have moved it 7 places to the right. I must have effectively multiplied by 10 to the 7 power. So I have to multiply by 10 to the negative 7 power to cancel that out.